All right, so thank you everyone for attending today's talk. Today we are more than happy to have Professor Chih-Cheng to give us the grand finale of our seminar series in 2024. Professor Hsieh received his bachelor, master, and PhD degree from the Department of Electrical Engineering, National Jiao-Tong University. And after that, he spent more than 8 years in the industry, leading a mixed-mode IC development department, developing CMOS image sensors for personal computer and consumer electronics. He joined the Department of Electrical Engineering, National Tsinghua University in 2007, and currently he is a full professor at the same department. His current research focuses on IC development for AI, IoT, biomedical, space, and robotic applications. He has served as associate editor in several journals, including IEEE Solid State Circuit Laters and IEEE Circuits and Systems magazine. So today he's going to share with us his recent work on processing in sensor technologies. Without further ado, let's welcome Professor Hsieh for his talk.
Okay, thank you, Professor Hsieh, for your kind introduction. Hello, everyone. Good morning. I'm Chih-Cheng Hsieh. And the topic I would like to share today is one of my research interests, which is the intelligent imager. Especially, we have proposed a terminology called processing sensor techniques. And I would like to spend today, I know it's about 20 to 30 minutes, so my slides more than that, so maybe I will skip some content, but I try to keep all the important insight of this topic. This is the outline. I will introduce first of all, I will do some brief introduction, and then I will introduce two topics related to the smart imager. One is the spatial domain feature extraction, and the other one will be temporal domain feature extraction. And then I will conclude some challenges and future prospects. CMOS image sensor market prediction is quite optimistic, thanks to the various application, including the mobile phone. Especially in the AI age, we have created some new possibility to integrate the processing capability with the sensing capability. So we can see the market forecast is quite good, and this is an interesting topic, and I think it needs more involvement and require more intelligent students in here. In AI era, we know we can separate the system to the centralized cloud to the edge devices. And each of them take care of a different task. In the centralized cloud, usually it will take care of the high-level processing and the complex task. But we need edge devices, because we need edge device to do the local and the real-time decision-making task. And we need to collect information data. And usually, you can only implement the low to mid-level processing capability in edge devices, and we need to consider the privacy issue. So that's why processing sensor is a very good candidate for the edge devices usage. What is the smart imager? I think the smart imager, we can see it can exceed the human eyes capability, because we integrate the conventional sensing capability with the AI computing, the intelligent capability together to tell what is the really meaningful information instead of only the raw image only. So we can say that you can exceed the human eyes capability to do the more things for various applications like automotive, mobile, security, and more. Let me introduce what's the difference of the conventional CMOS image sensor and what is the smart imager. From the upside figures, we can say in the conventional imaging system, usually there will be a CMOS image sensor, and then there will be some digital processor to handle the image processing for different applications. And in the conventional CMOS image sensor chip, usually we need a pixel array for sensing and then another circuit, especially A to D converter for the data digitization. After that, all the raw image will be transferred to the following digital processor and very high frame rate per second, full rate resolution, which means it's a very large data volume, and you will spend many power and the latency during the data transmission. This is the drawback of the conventional system. In contrary, we have proposed the smart image sensor, which means that we can integrate a new concept, which is the processing sensor concept in the CMOS image sensor. We expect the PI circuit can be implemented between the sensing pixel array and the data digitization circuit ADC. By doing that, we can dramatically reduce the required spec of the ADC block, including the data bandwidth, the resolution, and the power consumption. After the feature is be extracted, and then we only need to transfer the feature or the region of the interest data to the digital processor instead of the raw image. By doing that, the data, the bandwidth can be reduced, including the power and the mention rate. Latency, especially we can preserve the privacy. So all the issues we mentioned can be solved by introducing the processing sensor techniques in the smart imager system. Okay, the PI circuit technique can be implemented in different ways, from the near sensor processing to the in-column processing to the in-pixel. Basically, you can understand that through these three figures. The conventional architecture is the separated processing element with the conventional CMOS image sensor. You can integrate into a single chip. We call that a near sensor processing. But we can go furthermore to integrate the processing capability to the column level or into the pixel level. By doing that, we can increase the parallelism, we can increase the efficiency, and we can reduce the data transmission as mentioned. So it depends on your application. For sure, there is some drawback, design trade-off between the energy efficiency and the processing capabilities. When you do the near sensor processing, you gain the good processing capability and the programmability, but you will lose some energy efficiency. So use the pixel level PS. In the other way, you will get a different benefit and drawback. Okay. In the following, I will spend, I think, only a few minutes to introduce the spatial domain feature extraction and the temporal domain feature extraction. The feature extraction can be divided to spatial domain and temporal domain because we need information from these domains for different applications. For spatial domain, usually we will try to extract the relationship, the pattern between the spatial domain. For example, you want to get a shape, closeness, age, or something like that. And it can be applied to recognition, and based on the recognition to do many applications like fingerprint, retina, or biomedical diagnosis. And in the old technology, there are some existing techniques to do the spatial domain feature extraction, like the local binary pattern or the histogram of gradient. The local binary pattern means that you will do the comparison of a specific pixel and compare this pixel to its neighborship around a pixel to get a binary output. By doing so, you can get a pattern information of the spatial domain. That is called local binary pattern technique. And the other one is the histogram of the oriented gradient. It will do some gradient extraction and do some statistical result to get the histogram, and using the histogram to express the spatial information. All these two techniques can you can solve the background illumination variation issues because it only extracts the correlation relationship instead of the absolute brightness or darkness. So these two techniques is exist for a long time, but recently we would like to use the convolutional neural network. I think many of you may quite familiar with this technique. CNN can extract can do a very good job in spatial domain feature extraction by using the convolution operation and the ReLU and maximum pooling and so. So the concept we would like to share there, we try to merge these techniques into the sensor to see what can be done using a mixed mode circuit in the sensor architecture. So we start with the required operations of the neural network, including the MAC and the ReLU and the maximum pooling. The interesting thing is we find out that the MAC operation is can be easily implemented using the analog techniques. For example, the multiplication can be implemented using the current I equal to V multiplied by 1 over R, or the charge Q can be equal to I multiplied by T, which is the current integration. So the accumulation can be easily implemented using the wire sum in current domain or the integration of charge in Q domain. And the rectifier linear activation function value, can use a polarity check, which is quite commonly in circuit level, which is a comparator. And the maximum pooling can be easily implemented using a winner-take-all circuit, which means we find out that this operation can be implemented in mixed mode domain with high efficiency. That's why we start to develop some circuit techniques to do all these operations in sensor. Okay, so we can skip this one. This is one of our reported paper. We have proposed a convolutional CMOS image sensor, and we can implement the MAC operation with a different kernel 3x3, which is programmable, and you can integrate all this circuit, this operation into the color level, and to do the multiply and the summation operations. And we can demonstrate the result here that we can extract the edge, vertical edge, horizontal edge by implementing different convolutional kernels. This is a second architecture of the chip. We can see we have implemented a 3x3 subarray using the new pixel technique called pulse-width modulation. And we have implemented a 9-weighted current multiplication and accumulation. After that, we have realized the AD conversion. I can skip all the circuit detail. And this is the capture image. And we can see we can demonstrate the raw images and the feature images as well. And we have implemented the different kernels, and you can see the results. After that, we have a cooperation with Professor Tsing. Where is he? He's still behind here. And we use the capture image to train the model to do the 6 categories gesture recognition. And the resulting accuracy can be more than 95%. After that, we implemented another new work. We have implemented all the tiny CNN convolutional neural network into our sensor. And we have achieved the face detection task by using this sensor with the processing sensor technique. And we have separated the architecture into analog domain and the digital domain, and some of them in the mixed node domain depends on the required operation and what kind of circuit is the best candidate to do such a calculation. And we can see the resulting energy efficiency is quite dramatical because we had done the feature extraction before the ADC block, so the ADC workload can be effectively reduced more than 97%. And we have finished all the required operation for phase detection to output the result with 1 bit, which means that this is a phase, human phase or not. So if you implement all the function in our sensor, the only result you get is only 1 bit. So you can get a more than 99% data reduction. This is a chip photo and capture image. To validate the detection accuracy, we have tested more than 5.4K images with around 50% phase and non-phase distribution. And the result is quite good, and we have get the more than 93% accuracy. And this is a 2 example. One is the human face, the other one is not. So you can see we can get a feature and we can get a result. Okay, in summary, that this chip achieved the face detection task in micropower domain. And the required extra power to do the required operation of the neural network is around 36% compared to the raw image capture. Okay, the second topic is the temporal domain feature extraction. The temporal domain information means that we want to detect the temporal changes or temporal difference in each pixel, and report the label difference images or the location of the trigger pixel. The trigger pixel means that we can use the internal thresholding to check the temporal difference is higher or lower than the predefined threshold, and then we can transfer the label to the event. This is a different reporting system. And by doing so, you can see that basically it's a motion detection. So you can subtract out the static background and preserve the meaningful data only related to a motion. And it can be applied to different applications like motion, direction, saliency detection, and more. There are 2 main techniques to implement this temporal domain feature extraction. One is the event reporting. You can see from the video here that in conventional small image sensor, we basically use the frame-based operation. So we will do the exposure, real, and the report based on a certain fixed time interval, which is the frame time. So when you try to extract the motion information, the result will be discrete. But the event reporting technique, it use a continuous time detection. So you can report the continuous and the real time motion information of your object. This is its benefit. But it needs an in-pixel amplification and the in-pixel logarithmic sensor and the in-pixel comparator to doing such a task, which means the circuit is quite complicated, and you need a lot of power, and you need to deal some signal-to-noise ratio. The other technique is the frame differencing. It's based on the conventional frame-based operation to do the exposure and the integration. In conventional sensor, we convert the energy of the illumination to electronics. We need integration, or we need exposure to increase the signal conversion gain. So this kind of sensor, it doesn't need an in-pixel amplifier, but it has the drawback of the frame-based operation. And the required comparator can be merged into the pixel with the voltage buffer here. So in short, basically, frame difference in sensor has the benefit of smaller pixel, higher gain, but with the drawback of not real-time event reporting capability. Okay, so we have reported several papers in this domain. First one is the pixel level frame difference operation. We have proposed the ping-pong pixel to solve the conventional issue, which is parasitic unbalance induced error. So we use the ping-pong architecture to solve this issue and successfully achieve accurate frame difference operation and motion age reporting. After that, we have reported the improved work to modify, simplify the ping-pong pixel to using just one set of circuit to reduce the number of transistors in pixel with the proposed error compensation techniques. And by doing so, the pixel the pixel size can be decreased, the efficiency can be increased, and we also implement more function in this sensor. And we can do some simple comparison between these two techniques, event reporting versus the frame difference in operation. As mentioned, the sensing mechanism is quite different. For event reporting sensor, it needs a real-time logarithmic I to V conversion, and based to do the nonlinear high dynamic range response, but it needs the in-pixel amplification. And the frame difference sensor using integrating I to V conversion for gain, and it has a linear response. And the real mechanisms are also different. And the ER sensor needs a synchronous XY location report system, and the frame difference sensor use a conventional synchronous frame reporting system, which means when you consider the data compatibility with the following digital processor, the event reporting sensor has some difficulty to straightforwardly integrate with the conventional processing engine because the data formats are totally different. In contrary, the frame difference sensor can be compatible to the existing data processing system. Here shows a simulation the simulation video to demonstrate the difference between these two kinds of sensor. And you can see in the low contrast region and the DBS sensor, event sensor, the performance is worse than the FD sensor. But if we apply a sliding dark zone to simulate the low illumination condition, we can see the result become different. The motion detection sensitivity of the DBS sensor becomes better compared to the FD sensor. I think that's because the logarithmic sensor conversion property. And the event sensitivity can be improved using different techniques, very techniques including the adaptive thresholding or the multiple exposure or multiple gain. But there comes with a different trade-off, including when you apply a smaller threshold to get a higher motion sensitivity, you will get a higher noise. So it all depends on the required signal-to-noise ratio and your applications. And talking about the real speed comparison, as mentioned, the output of the event sensor is the XY location instead of the pixel level or the pixel event. So it needs a certain period of time to do the event accumulation to get the meaningful spatial information. You can imagine that basically it's a continuous reporting system, and in each time stamp, it can report only one XY address of the event. So you need a specific time to do the accumulation to understand what you are looking right now, what's the shape of the moving object. On the contrast, the frame difference output is quite straightforward. You can see all the information like this one. So this slide demonstrates the accumulation result of the event sensor and the one frame result of the frame difference sensor. So you can see you need accumulation for the event sensor to get the similar output of the frame difference sensor for the following digital processor. Okay, there are some challenges because we propose a processing sensor technique based on the analog and the mixed mode approaches. So it comes with some limitation, including the low to mid-level processing capability and limited accuracy and flexibility. And it should be implemented based on the application-driven task. It cannot serve as a general-purpose solution because we chase for the extremely high energy efficiency comes with the price of the limited processing capability. But it has the benefit of the high parallelism and the low latency, so you can implement it in the edge devices to get the real-time data collection and decision making. And if you want to get a higher energy efficiency, maybe you can start with some modeling and some power management tasks in system level. For example, you can combine with the tiny CNN network or spiky neural network and to solve the limited processing capability. And you need pay more attention here is that you need to consider the data retention issue in analog domain. And the other one is the pitch limitation. Because you integrate more circuit into the pixel, you will increase the sensing area, which is not good for the pure image sensing. But it can be solved by using the 3D stack technique like a 2.5D or 3D. The last one is the energy harvesting. You can use energy harvesting to improve the system level energy efficiency, or you can do some power management techniques. Okay, let me conclude my talk. And I think the evolution from IoT to smart AIoT is happening. That means you will transform the raw image data to a meaningful data before the following data processor. And the data processing and the decision-making tasks are moving from centralized cloud to edge devices, as mentioned, to solve the data bandwidth, speed, power consumption, and the privacy issues. And we have demonstrated the mixed mode processing sensor operation is energy efficient for specific tasks, but with a limited flexibility. And advanced packaging technology can help the processing capability and the integration level. And finally, the last one is the application-driven intelligent vision system. Is using processing sensor technique is a promising solution, and we believe that it will be a main technical trend in the near future. Thank you for your lesson.
Thank you, Professor Hsieh. Any questions from the students or audience? One thing I noticed, a very quick question.
Sure.
One thing I noticed is that after we use your IC, right, so we're going to send a feature instead of the raw image.
Yes.
Would it improve the privacy concern or mitigate the privacy concern for all the, such as webcam or surveillance camera?
Yeah. Okay. Thanks. You. Very nice question. We can see that we try to extract the motion information or the spatial edge only instead of the raw images, which means you cannot see the detail of the privacy-related information in this kind of output. That's why we say that by using the processing sensor technique, you can solve the privacy issue. Yeah, and this concept has been widely acknowledged that from different research groups. They are quite interested in this concept, and they would like to have more discussion and collaboration with us. Yes.
Thank you. Any other questions? So if not, then let's thank Professor Hsieh again for his excellent talk.
Thank you all.
This concludes today's seminar talk. Thank you, everyone.